Hello everyone, this is going to be our notes on day 2 of solving trig equations. So we're going to see similar stuff, similar type problems that we saw last time, some different type of techniques and maybe some more complicated answer sets, but same type of problems here. So again, we are going to solve over specific intervals. If we have a theta, we'll use degrees, and if we have an x, we'll use radians. So let's start, as we usually do, with number 1. This one should seem relatively familiar. We're going to work backwards as we normally would. Divide by 4. And then I'm going to take the square root of both sides. So I will have sine of 2x equals plus or minus root 3 over 2. At this point, I'm feeling pretty good about things. I'm feeling good about things because that number there, that root 3 over 2, shows up on my unit circle. So I'm going to keep going, and I'm going to say, well, 2x equals So the values that we're looking for, the values on our unit circle where the sign is positive or negative root 3 over 2. So that's going to happen at 4 places on our unit circle. Pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Remember from last time, when we have a multiplier here, that serves as a horizontal compression. So this means we are going to have 2 rotations around the unit circle because we will divide our values, and in essence, we're going to have twice as many solutions as we expect. So our second time, I'll change the color here. Our second time through the unit circle, we're going to have 7 pi over 3, 8 pi over 3, 10 pi over 3, and 11 pi over 3. Why do we have to do all that? Well, because these are the possible values of 2x. Now we want to find x, so what we'll do is we'll divide each of those 8 answers by 2. So our actual 8 solutions here are going to be pi over 6, pi over 3, 2 pi over 3, 5 pi over 6, 7 pi over 6, 4 pi over 3, 5 pi over 3, and 11 pi over 6. It's a lot of answers. We end up with 8 answers here. How could we make sense of that? Well, a sine function that's not one of our cardinal directions, our quadrantal angles, are going to have 2 solutions most times, right? One in for sine, one in the first, and one in the second quadrant. With our plus or minus, now we have solutions in quadrants 1, 2, as well as 3 and 4. So now we're up to 4 solutions. And then we also had this multiplier here, this the 2x, the double angle in the sine function. So that means we had to go around the unit circle twice. So we had 2 solutions that got doubled to 4 with the plus or minus, and then those 4 solutions got doubled to 8 with the double angle. All right, so let's move on to number 2 and see what's going on here. All right, on number 2, this is a similar problem to what we saw last time. I don't like having the cosine and sine functions in the same place, but cosine 2x is rewritable using our double angle formulas. I'm going to rewrite this as minus 2 sine squared x plus 7 sine x plus 3 all equals 0. What allows me to do that is our cosine double angle property. So I'm going to factor this, and I'm actually going to move everything to the right side of the equation just so my leading coefficient is positive. So I'm going to have 2 sine squared x minus 7 sine x, and we had 1 and 3 is 4. Now that becomes negative 4. Oh, we already have an equal sign. We don't need an extra one. So now we've manipulated this using our trig identities in a way that allows us to solve through factoring. So I'm going to factor this. 2 sine x and sine x will be our leading terms in each of the binomials. We'll need a minus 4 over here and a plus 1. That'll get me negative 8 sine plus 1. That's my negative 7 sine, and we're getting somewhere. Now, there's not going to be any solutions coming from this factor over here because the range of sine just goes from -1 to +1. We will get a solution with our first factor, where sine of x will equal -1/2. On our unit circle, those are going to be the values in the third and the fourth quadrants, where we are 7 pi over 6, and 11 pi over 6. So this problem, even though it looked a little bit more complicated than our first one had 8 answers, and this one just had 2. I think it's worth mentioning here, you can't really judge a book by its cover here. We're going to have different amounts of solutions. We don't always know what we're going to have, what we're going to end up with. Let's move on to number 3. This is one of our co-functions. All right, so this tangent of 90 minus x, that is exactly the same as the cotangent of x. And I know that cotangent of x is really the same as cosine x over sine x. So really, I'm trying to figure out where cosine x equals 0. So where cosine equals 0, that happens at 2 places, either at pi over 2 or at 3 pi over 2. Now this one, I don't know if it should have been in degrees. If it should have been, let's change it to a theta here, and our 2 solutions would be 90 and 270 degrees. Good. That one's pretty straightforward with a quick switch of our function using our co-function identity. It allows us to solve a little bit more quickly and directly. Let's move on to number 4. So as we look at number 4, I recognize this as one of our identities. I see this as our sine of theta over 2. And that means if that value is set equal to 1, there's only one angle where sine equals 1 on our unit circle. That happens where theta equals 90 degrees. In this case, though, our argument is theta over 2. So we'll have to double that angle. Theta will equal 180 degrees. That's not the only way we can solve this. Let's say we didn't necessarily recognize it as an identity. We could solve this algebraically as well. I'll use a different color just so we can make sense of it. If we were to square both sides, we would get 1 minus cosine theta over 2. All equals 1. We can keep chipping away here, double both sides. 1 minus cosine theta equals 2. Subtract 1 from both sides. Negative cosine theta equals 1. So cosine theta would equal -1. Well, where does that happen on our unit circle? Where does cosine equal -1? That happens at 180 degrees. Look at that. Either way we solve this, we get to the same answer. All right, we're going to keep moving along here. Number 5 is a little different. We have that 3 theta inside our parentheses. That's something that we don't see quite as often. Usually we only have 2. So maybe our instinct here is we're going to end up with a few more answers than we usually see. But luckily, this is a cosine problem, and it is a cosine set equal to a unit circle value. I think the best move for us here, just because of the complexity, right? We have 2 operations going on. I'm going to use U substitution. 3 theta minus 15. So what that means is that we can rewrite this as cosine of u equals √3 over 2. Our solutions on the unit circle for u would be at 30 degrees and 330 degrees. Remember, this 3 tells us how many times around the unit circle we should go. So not just 30 and 330, we'll also include 390 and 690. And then finally, on our 3rd time around the circle, 750 and 1050 degrees. Why are we doing that? Because we know that u is the same as 3 theta minus 15. So we know that 3 theta will be the same as if we added 15 degrees to each of these 6 solutions. So we'll have 45 degrees, 345 degrees, 405, 705, let's see, lost my place here, 765 and 1065. All right, now we're getting closer to an answer. These are our values for 3 theta. Now to solve this, we're going to divide all our answers by 3. So our 6 legitimate solutions are going to be 15 degrees, 115 degrees, 135 degrees, 235 degrees, 255, and 355. What's nice about this, we can see, right off the bat that we are within our range, right? Our domain. Our smallest angle is pretty close to 0. Our biggest angle is very close to 360. It is unlikely that we would have missed any angles if we're hitting those both ends. So that is a excellent opportunity for u substitution. And number 6 is also a great opportunity for u substitution based on how it starts. Sine of 4x, that looks a little complicated to me. I want to simplify that down, so I'm going to let u equal 2x. I can rewrite this problem as the sine of 2u equals the cosine of u. This affords me some opportunities here. Now I can expand using my sine double angle to sine u cosine u. And I'm going to subtract that cosine u and move it over to the left-hand side of my equation. That way, the equation is set equal to 0, and I can solve through factoring. I'm going to solve factor out cosine u, and I will have 2 sine u minus, I forgot my u, minus 1 in the parentheses, all set equal to 1. I think now is the best time to convert back. We're going to have cosine of 2x equals 0, and we're going to have sine of 2x equals 1/2. So we're going to solve these as we normally would. I'm thinking about cosine equaling 0 on the unit circle. That happens when x is 0 on our unit circle. So that happens at, so where 2x is going to equal pi over 2 and 3 pi over 2. I have a 2 there. That tells me I need to go around the unit circle again. So I'm going to include 5 pi over 2 and 7 pi over 2. We can finish these solutions here, divide everything by 2. We'll have pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. If we move over to the right, let me change color so we can differentiate here. We have sine of 2x equals 1/2. 1/2 is on our unit circle, so we know that 2x must equal pi over 6 and 5 pi over 6, as well as their coterminal angles, one time an additional rotation around the unit circle at 13 pi over 6 and 17 pi over 6. These are values we are going to divide. So our resulting solutions here will be pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. Just as a last check here, I would just make sure that we're verifying that all our answers are on our specific interval. 17 pi over 12 is a strange angle, but it is less than 2 pi, so no problem there. All right, we can turn over to the back, and we have, it looks like 4 more problems. I think I would like, you know what, we're going to keep just approaching this the same way that we have been. I'm going to just guide you through each one of these, and we'll keep moving. So here, the copier ate this up a little bit. Let's see. Should look a little bit more like that. Let's see if I can get a little fancy with it. Oh, who cares? So we have sine of theta divided by 1 plus cosine theta. I don't know if that helped or not. This is a tricky one. I'm going to start by multiplying both sides, getting rid of my fraction. I will have sine theta equals 1 plus cosine theta. And at this point, I'm feeling a little unsure. I'm not quite sure where to go. There's not much I can do with sine. There's not much I can do with cosine when they're to the first degree. So if I square both sides, something we haven't seen a lot of, it will open up some options to us. So I'm going to have sine squared theta on the left, and on the right, I'm going to have 1 plus 2 cosine theta plus cosine squared theta. And the reason I like that, this allows me to rewrite things using our Pythagorean identities. I can get everything in terms of cosine. So I can rewrite sine squared theta as 1 minus cosine squared theta. And I'm going to just rewrite everything else we have here. And then from here, I want to group things, and I think I'll be able to solve this through factoring. So I'm going to set one side of my equation equal to 0. I'm going to have 2. Oh, excuse me, that doesn't make any sense. If I subtract 1 from both sides, the 1s will cancel here and here. If I add cosine squared to both sides, I will have 2 cosine theta plus 2 cosine squared theta. That's a nice easy factor here. 2 cosine theta comes out, and we're left with 1 plus cosine theta in the parentheses. We will get theta equals 90 degrees. Right, that's where 2 cosine theta equals 0, as well as where cosine equals negative 1. Well, let's see, sorry, cosine also equals 0 at 270 degrees, and cosine equals negative 1 at 180 degrees. Now, this is important. We squared something, right? Up here, this is a move that can cause some complications. When we square things, we introduce the possibility that we have multiple solutions that don't really fit the problem. When we square things, we eliminate the possibility of positive and negative answers being different, right? We really mess things. We really mess with things. So what we need to do, if we square something like we did at this step here, we need to check all of our answers. So I'm going to plug those back in. Sine of 90 over 1 plus cosine 90 equals 1. I'm trying to check that. Sine of 90 is 1 over 1 plus 0. That one works. If I tried 270, I'd get sine of 270 over 1 plus cosine 270. Sine of 270 is negative 1. And then our denominator there would become 1 plus 0 or 1. This solution does not work. 270 is extraneous. Finally, our third possibility here, sine of 180 over 1 plus cosine of 180. This would leave us with a numerator of 0, which is definitely not going to be set equal to 1. I believe our denominator would also be 0. So 180 is also an extraneous solution. The only good answer here is 90 degrees. So when do we have to check for extraneous solutions? When we square both sides of an equation, we introduce the possibility of extraneous. If you think back to Algebra 2, the other place we see extraneous solutions is when we square rational functions, square roots. Right? We create answers that technically are true but are not in our domain, so must be excluded. Let's move over to number 8. When I look at number 8, that looks like a factoring problem to me. It looks quadratic. So I'm going to directly factor here cosine of x plus pi over 4 and cosine x plus pi over 4. And now I'm going to use my coefficients, numbers that add to 2 and multiply to negative 3. That's going to be positive 3 and negative 1. Well, I know that cosine will not get us to an answer if it's set equal to -3, this will not create a solution. However, on the right, I should be able to get a solution. I'm trying to figure out where the cosine of x plus pi over 4 equals 1. Well, that happens when our angle x plus pi over 4, excuse me, let me reset that. Cosine equals 1 at an angle of 0, or 2 pi. So the way we're going to approach this is we're going to write both of those solutions. I really recommend doing this. It's always easier to exclude a solution that doesn't fit than to try to find one after the fact. So if I were to subtract pi over 4, I would get negative pi over 4 for one solution, and my next solution, 7 pi over 4. Remember, our domain for these solutions is 0 to 2 pi, so this 7 pi over 4 is our only good solution. All right, let's finish up these problems involving calculators. So again, we're in this form where we're thinking about factoring. I can't really factor to start here because I have secant squared and tangent. So I'm going to use my my Pythagorean identity to rewrite secant squared as 1 plus tangent squared theta minus tangent theta minus 4 all equals 0. I'm going to combine my like terms. So I am in a form that looks more familiar, in a form that will allow me to factor. So I have tan squared minus 2 tan theta minus 3. That is factorable into tangent theta minus 3 times tangent theta plus 1. This means that tangent theta can be set equal to 3 and tangent theta set equal to -1. These are values that are going to be a little bit difficult. One of them is not on our unit circle, that +3. So we'd have to go to our calculator, make sure we're in degree mode, and use our inverse tangent function. In this case, it would tell us that our angle is 71.57 degrees. But we need to remember that the period of tangent is just pi, or 180 degrees. So what we need to do to find an additional solution on our interval is add 180 to our angle 71.57 degrees. This second solution will be 251.57 degrees. So this particular part of our function generates two solutions. And then we're going to do the same thing with tangent theta equaling -1. Well, that's a 45-degree reference angle. We know that tangent equals +1 in the first and third quadrants at a 45-degree angle, and it'll equal -1 in the second and fourth quadrants at the same reference angles. So where does that happen? This happens at 135 degrees, and it happens at 315 degrees. So those are our four solutions. Just in the same way that we have multiple answers on our unit circle, when we use our calculator, we need to account for those multiple answers since our calculator uses our inverse relationships that have more limited domain even than our answer sets. Let's look at one last problem here, and we'll finish up our notes. I know 11 is going to be relatively quick. Here, I have another situation where I can solve through factoring. 3 cosine x minus 2 times 2 cosine x minus 3. Right? I'm factoring this just as we would a quadratic, and just working through guess and check to try to find combinations of numbers that work for us. All right, so now we're factored, and now we can start to solve. So over on the left here, we're going to have the cosine x equals 2/3, and on the right, cosine x equals 3/2. This makes things easier on us. That 3/2 is outside of our range, so this will not lead to a solution. However, the cosine of x equaling 2/3 will. that's something we're going to use our inverse cosine function with on our calculator. So our inverse cosine, and we're going to plug in 2 over 3. And what we get for x there is 0.84. Yeah, I'm just making sure I had that rounded correctly. Now, we know that cosine is positive on both on the right side of our unit circle. So this value, this 0.84 radians, is in our first quadrant. So what we need to do is to find the other answer on our unit circle, unit circle with the same reference angle as this one here. So what our second solution will be is 2 pi minus 0.84. The reason we're going to subtract from 2 pi is that that will allow us to achieve the same exact reference angle in the fourth quadrant, the other quadrant where cosine is positive. When we plug that into our calculator, we end up with an x value of 5.44. So 0.84 is one solution, and 5.44 is our other. The last problem is a system of equations where they tell us y equals sine 2x equals yx. I think I'm going to create a separate video just to give you guys some guidance on solving through graphing. So we'll wrap things up with number 10. Thanks for your attention, everybody.